to work with these new variables that we're introducing today. So we have a lot of objectives and we're going to go pretty fast. We want to define gravitational potential and gravitational potential energy. We've actually already defined gravitational potential energy. We want to state and apply the expression for a gravitational potential due to a point mass. We want to state and apply the formula relating gravitational field strength, one of our topic 6 variables, to gravitational potential gradient. We want to determine the potential due to one or more point masses, and then solve problems involving gravitational potential energy and gravitational potential. I do not think we'll get to these final two. There's actually 2 more objectives beyond these for topic 9.2, but it's quite possible we're not going to get to these 2 drawing objectives today. So last we met, which feels like it was forever ago, we did talk about gravitational potential energy, and we said that we've never truly calculated a gravitational potential energy before. It is not mass times gravity times height, because height is extremely arbitrary. We have many times calculated a change in gravitational potential energy, but that's insufficient for us in this topic. We did define gravitational potential energy in terms of work, and we said it was the work done in moving a mass from infinity to its location in a gravitational field. We also talked a little bit about that's a difficult thing to calculate, because as we move from infinity to closer, the force is not constant. The force is also impacted by how far we are from the source of the field. One of the other things that we mentioned last time was we can move from one location in a field to another, and the amount of work required to do that is independent of the path that we take. So it should take the same amount of work to move from spot A to spot B if we make a few stops as if we went directly there. So all that matters is really how far we are from the source of the field at the beginning and at the end of our trip. And then we also did, well, we laid down the groundwork to be able to quantify gravitational potential energy. We said that we're going to set a value of 0, meaning no potential energy, to be when we are infinitely far from our source of the field. Right? But we also know that when we're closer than infinitely far, we have less potential energy. So all gravitational potential energies that we ever calculate from this point on will have negative values. Right? So we will never have positive potential energy. We'll always have negative. But remember, it is kind of arbitrary. The only reason for that is we're setting infinitely far away to be our reference level, because, well, especially when Lane's not here, we can't really have arguments about how far infinitely far away it is. All right, so our equation for potential energy, which we saw last time, but we didn't really get to appreciate it, does come from our definition, right? Where work, we've been saying for probably 18, 20 months now, is equivalent to a force times a displacement, as long as the direction of the 2 are the same. And the type of force that we're talking about here is our gravitational force. So that's our Gmm over r squared. Right? And if we move to a location in the field, the displacement we're talking about, and this is a little bit disingenuous, but the displacement that we're talking about, or at least that we would measure, would be based on how far we are from the source of the field. So this is actually going to be the same thing as the distance we are away from the source of the field. Right? And work is now our same thing as potential energy, right? That is the work done in moving something from infinity to where we are is the potential energy. So our good equation for potential energy, right, just has this r canceling out one of these. So it's just Gmm over r, or what did I forget? The negative sign, right? Because every potential energy we calculate is going to be negative. Okay? Is that in your data book? Is it in your data book? Stay open to topic 6 and 9. We're going to be hitting all of those equations on the left-hand side today. No, it's not. It's not there. Okay? It's not there. Now, I'll show you a trick to get it in a few minutes, but it's actually not there. All right? So that's really the end of the story when it comes to gravitational potential energy. So our next variable, which is actually still on our first objective, is something very related but different called gravitational potential. And you might be having like a deja vu moment because we kind of did this last year. We went from electric potential energy to electric potential difference all in the same day. And now we're just doing all of that in 10 minutes instead of in a few. So just like electric potential is the energy per charge, gravitational potential is the energy per unit mass. Right? That is not the definition. Right? It's not our official definition. What gravitational potential is how much energy something has per unit mass. So what unit should it be measuring? Energy per mass. So again, joule per kilogram. Right? Joules per kilogram. Right? And just giving that meaning symbolically, gravitational potential, which is a capital V, just like electric potential. Why would they? Well, it's the same thing. It's just energy per unit mass as opposed to energy per unit charge. I think they're nice in doing that. I don't think they're nice in doing that. So gravitational potential is the gravitational potential energy per unit mass. Is that one in your data booklet?
Yes.
I think it is. I think it is.
Okay.
All right. Right. Yes. Right. Sure. As long as the mass doesn't change, then yes, we can put a delta in front of both of those. Now, what we just derived was that potential energy is negative Gmm over R. So we can actually come up with a different expression for gravitational potential. So negative Gmm over R, but divided by M. So another way of finding gravitational potential is just negative Gm over R, where G is our gravitational constant, M is the mass of the thing producing the field, and R is how far away we are from the thing producing the field. Is that yes? Okay. So here's the trick that I referred to earlier, and then I'll take a timeout for a minute. If we know this, and we know this, then you have this one, right? Right? You have that. Because potential energy would be the gravitational potential multiplied by the mass. So all we have to do is throw, attach the little m to this guy. And then that changes this into potential energy. So yeah, it's sort of there for you, but Ivy's just saying, yeah, you need to work a little bit in order for us to get that to you. Yeah.
Is gravitational potential also always negative?
Gravitational potential should always be negative, yes. All right, other questions at this point before we keep moving along? All right, again, I fully admit these are a lot of interrelated, very similar variables, and I don't expect you to be to be happy with these, well, certainly not at the end of today, probably not ever, but we are going to have, we don't have a whole lot more to do really besides these objectives. We repeat them all for electric stuff, and then we have like 4 more objectives beyond that. So we're going fast through the material so that we have the opportunity to kind of slow down as we use this stuff. All right, so official definition, then we'll move on to our final variable for today, is essentially the same definition as gravitational potential energy, but we throw in a per unit mass, right? So potential energy was the work done in moving from infinity to the spot. This is the work done per unit mass in moving from infinity to that spot in the field. All right, so another thing, and really this is almost the last thing for today. We had an objective involving something called gravitational potential gradients. So I must have been a little bored last year or the year before because I have a lot more images than usual that relate tangentially to the material. Where would we be likely to see a sign like that? if you're like driving and you're approaching like like a hill, or not a hill, like a mountain, or like just any kind of incline, right? There might be a road sign that just warns you, hey, you're about to go up, maybe go a little faster before you get there, so you have enough momentum to get you to the top. But that 10%, we would say that's a 10% grade. And what a 10% grade means is, right, maybe we have 1 kilometer, right, like horizontally. While we're traveling that 1 kilometer horizontally, we're going to go up a tenth of that, 100 meters. Instead of saying kilometers, I should say 1,000 meters, right? If we're going horizontally 1,000 meters, we're going up 100 meters. That's what a 10% grade means. And we can call that a gradient, and all that a gradient means is how much we're changing something as we move spatially. And that's what a gravitational potential gradient means. It means what is our change in gravitational potential, delta V, per spatial distance that we're covering. So delta R, how far we've moved, how much further we've moved from the source of the field, or how much closer we are from the field. Okay, so delta V over delta R is called a gravitational potential gradient. What was this little g again? Told me earlier? Gravitational field strength. Okay? So this is the link between our topic 6 variables and our topic 9 variables. Gravitational field strength is equivalent, it's equivalent to the negative of the gravitational potential gradient. There are very few questions I've ever seen that have us use that expression. It's actually a pretty common expression to use when dealing with electric field strength. Alright, so again, gravitational potential gradient is just referring to the change in gravitational potential per spatial change. Alright, last thing I have, before we start working with some of this stuff for most of the rest of the period, is, well, good news, right? Gravitational potential, really our only new variable for today, is a scalar. Okay, so that means that if we have multiple gravitational potentials, we just literally add them together. We don't worry about vector addition, we don't have to worry about, does this one point that way and the other points the other way, do I subtract them then? No. You always add. Okay? Gravitational potential has no direction associated with it. Okay. So, what I'd like to do in your two-sums and four-sums and three-sum is work with some of these new variables and some of these new expressions. So we have about 40 minutes left. I would like to accomplish our 2 drawing objectives. So get help with this as you need it. I do have answers at the bottom. However, number 2 has the wrong answer. So I'll give you the right answer. And then I don't think that you'll actually finish all 6.